Hello everyone and welcome to another session of Digital WE Days. My name is Ida Son and I will moderate this webinar today. Our topic of today is ICeGaN in LLC Converters, unlocking performance behind silicon for next-gen power systems. Our speaker today is Carlos Toyos Bada from Cambridge GaN Devices. Welcome, Carlos. Cool to have you here. ICeGaN pushes the limits of high power conversion with minimal losses and high switching speeds. But what makes it outperform SiC and discrete GaN? So let's find out. Stage is yours. Have fun, Carlos.
Good morning, afternoon, evening, everyone. Thank you all for attending this webinar, and many thanks in particular to Purza Electronic to give us this opportunity again. So I am Carlos Toyos Bada. I am part of the application engineering team here in CD, and today I will take you through the benefits of using our products in high power, high frequency LLC converters. This is the agenda for today, so I'll briefly touch on what is CD, who we are, what we do. I'll remind you about the benefits of GaN against traditional silicon. I'll explain what ICeGaN is, and then I will talk about the LLC and the benefits of using our products in this topology. At the end of the presentation, I will briefly summarize experimental results of a 3 kilowatt LLC converter that we run here in the lab. CED is a young and dynamic company. It's a fabless company, fabless semiconductor company. Our headquarters are in Cambridge in the UK, as well as the main R&D site. But we have offices around the world. We have presence in the main markets in North America and Asia. We have experienced significant growth in the last 4 years. We're still growing. We are about 60 employees, and innovation and knowledge is in our core. Actually, we spun off from the company spun off from the University of Cambridge. We started a few years back with higher RDSON devices targeting the consumer market, but then through the years we moved into the industrial and data center market because we now have lower RDSON ICeGaN. And in the near future, our plan is to develop ICeGaN for automotive. So data center and automotive is relevant markets where I think the LLC is a very important topology. Why GaN is the future? Let's take here a moment to compare traditional silicon devices with gallium nitride. Silicon is slower, has higher driving losses, is less sustainable, and on the other hand, GaN has lower output capacitance, lower output capacitance charge, lower gate charge, has no reverse recovery, and has lower RDSON per area. And its manufacturing process is also more sustainable. This is something that many of you might not know, but the GaN hemp fabrication avoids some of the processes that are that silicon needs, and these processes are high carbon emission processes, and so that GaN devices achieve lower per device carbon emissions compared to silicon. And here is a chart that we have developed internally, and then you can see also this in our ESG report of this year. Why ICeGaN? What makes ICeGaN the right device for an LLC? So we said that GaN is faster than silicon, and you can have shorter dead times. You then can increase the frequency and that allows to higher power density converters. On the other hand, GaN is traditionally difficult and complex to drive. We have solved this problem here in CGD. So our ICeGaN is easy to drive. Here is what is inside our chip. So it's built monolithically. As you can see, it's a power HEMT and there's some circuitry inside. This circuitry allows you to drive our device from 9 volts to 20 volts, and the threshold gate voltage is 3 volts. So it means that you can drive ICeGaN with a standard MOSFET driver. There's no problem about that. I will show you later. And the one of the main benefits of ICeGaN is that it has a Miller clamp inside. So it's very important for dV by dt, and the Miller current will be going through the gate to the source, because this Miller clamp, once you turn off the device, it pulls the gate down to the source internally. So the current, the parasitic current, never goes out of the device. Our device is very robust in all pins, and also particularly the gates can handle voltage overshoots up to 80 volts. Here is our ICeGaN portfolio. The most relevant devices for high power converters are the P2 series devices. We have a 25 milliohm, a 55 milliohm in a 10 by 10 millimeter package. It's a bottom side cool package, and you have them commercially available. If you want more info, you can visit our website, or you can contact us directly if you like. And let's start with the big advantage of ICeGaN versus discrete solution. So the discrete GaN are very complex to drive. So they need more external components due to the threshold voltage. They need more. They need negative drive, and they actually also require tight PCB layout. You have to do the layout very, very tight and put some effort on it. On contrast, our ICeGaN has solved this problem, in particular having the Miller clamp inside. And we only need one resistor, we only need one capacitor per device. We don't need negative drive, even with hard switching applications like totem pole PFC. And actually the LLC is a soft switching application, but there will be moments like a startup situations like dynamic load in which you can maybe lose this soft switching. So you might need negative drive if you use discrete GaN for LLC. Also, because we have the Miller clamp, the layout for us is more flexible, so you have more PCB space available, for example, for cooling. And we can, as we will see, we can use a bootstrap, and there's no problem with OBP or UBLO in the drivers. So here is our real board. Is one of the boards we have in the lab. So we developed a 3 kilowatt LLC converter. It's a full bridge in the input, but this full bridge is divided into half bridges, and this is the dot card of one of these half bridges. So as you can see, the schematic, 2 devices, 1 resistor, 1 small cap to on the BDD pin. The BDD pin is simply tidy up to the BDD of the driver, and on the right, you can see that the driver is quite far from the ICeGaN, so the gate path is very long, and we are switching at very high frequency, and we don't have any issues with that. One advantage that might be good for high power applications is just the paralleling ICeGaN. So paralleling ICeGaN is very easy. We have tested in the lab up to 5 devices in parallel. They share current really well, and because our ICeGaN has very low gate charge, then you don't have to do anything else. You can parallel the ICeGaN and use a driver. So some of the GaN competitors, they only allow you, I think, up to 2 devices, and if you use silicon devices, then you might have problems with the coping with the current. So the driver might not cope with the current that has to provide, so you might have to add some boosters and extra components to drive parallel silicon MOSFET. So here you can see a chart of the gate charge using 1 device, or 2 parallel or 4 parallel, and it's significantly lower and makes the life easier. I think this is important for high power converters. The LLC and the beauty of the LLC is that is a sub switching application. So the main losses are conduction losses, has very low switching losses, and to drive in nominal conditions and to achieve that, you need 0 voltage switching in the primary. So you achieve 0 voltage covering in the secondary, and if you drive it correctly, there's no capacitive mode operation. If you go into capacitive mode operation, means that you will lose the 0 voltage switch. So the LLC converter is basically a voltage a square wave generator driving a resonant tank, and then you have an output rectifier. The output voltage is regulated by the switching frequency with 50% duty cycle, and the resonant tank design determines the operating frequency. Must be dimensioned to ensure the converter can deliver full load across the entire input voltage range. There might be different design strategies for all the LLC design. This slide gives you an overview of the resonant tank design process for a LLC converter. So this might vary depending on the application and what you want to achieve. So we start with the specs, the voltage, the power, and the size, which define the design boundaries. Then we move into some initial considerations where we might choose the topology, full bridge, half bridge, and roughly estimate maybe at this point some losses in the magnetics and also in the primary bridge. So a key and also in the output rectifiers. A key decision here is the selection of the primary switch. This is not only about conduction losses and driver selection, it directly impacts whether you can achieve 0 voltage switching at high frequency. So especially we need to choose a switch with a low RDSN to minimize conduction losses, and a combination of low output charge and magnetizing inductance to ensure there's enough energy enabled for 0 voltage switching during the dead time. And estimating the conduction losses on the switches and the primary switches is very straightforward. It's just you can do a very quick simulation and get your RMS value through the switches, and you calculate the losses, and then this can be you can do a very small exercise to do the losses in each device, but also the losses in the bridge, whether you choose full bridge or half bridge. This is what you see in this table. So it's a comparison between our devices and different configurations. So the first thing to analyze, and the most important and challenging part, is to design and dimension the three components of the resonant tank. This resonant tank has to be designed such as the converter is able to operate full load conditions and that the full input voltage range and allows 0 voltage switching, as we said. And we must about, as I said, capacitive mode, because if we are entering capacitive mode, we will lose 0 voltage switching. So averaging methods that apply for PWM converters cannot apply in this topology. It's a resonant topology, and you might know that the most popular approach is the first harmonic approximation. So this is the gain equation. So the voltage gain equation. So you move the frequency, and then you with the frequency you took the output voltage. So the gain equation cannot be solved analytically. Yeah, we use the graphical interpretation of it and tune the parameters until we get the resonant tank values. So the design is very delicate. There's multiple parameters here, but basically you have to tune Q and these two parameters are the most important to tune the LLC to operate a full load with the voltage gain range. So if we increase the frequency and we keep Q constant, then we can reduce the resonant inductance and also the magnetizing inductance. And then later maybe we can adjust Q and M to even increase the magnetizing inductance, and then we can reduce the circulating current because the GaN output charge capacitance is much smaller than silicon devices. So this means we have less energy storage in the inductors, and that is important to reduce the size of the magnetics. So a little briefing about the magnetics is that inductor design is all about the energy storage. So if we reduce L and we keep the number of turns and the flux density reasonably the same, we can reduce the effective area of the core, and hence we can reduce the size of the magnetic. So this is a hint that is our first hint to really see that if we increase the switching frequency, we can reduce the magnetic size. And of course, the magnetic design is very challenging. There are many trade-offs. So it depends on your goals or what you want to achieve with the LLC. If you prioritize efficiency or you prioritize power density. And also, as smaller volume magnetics means cooling is more challenging. If you increase the frequency, then you will have more losses in the core and more losses in the winding. So iterating and finding the balance between size loss and thermal management, and it's a key to reduce the magnetic size for high frequency LLC. So I put here I want to mention here the one tool that is free and is a fantastic tool developed by by Alfonso de la Torre is open magnetics, and it helps you to iterate much faster. It's really a really good tool. You can choose the core, you can choose and define your windings. It gives you some initial values for losses, and it's great. So the even if you don't have any output loads, you need to have circulating current in the LLC, which is the magnetizing current. And this magnetizing current must be high enough to maintain 0 volt switching, and is the current that actually discharges and charges the COTR. So that dictates how long the 0 volt switching time and the dead times are. But also this current has to be low enough to avoid excessive losses. As you will see, this is a great advantage of the GaN devices, because the QSS is significantly smaller than MOSFET. So one thing here what I want to mention is don't use the COSS value to estimate the 0 volt switching time. Use the COTR or use the QSS. So basically the COTR represents the drain source charge, and it's usually in the data sheet at 400 volts. So it's very useful, this value for the, so you don't have to do the numbers, you just use this value. And even the MOSFET has larger figure of merit RDS-on COTR, and that kind of actually limit the RDS-on of the MOSFET that you want to choose, because if you want to a very low, if you need a very low QSS in a MOSFET, then you're limiting the going to a lower RDS-on, so you are actually limiting the ability to decrease the conduction losses, which are the major contributor in the LLC converter. So what we saw here is a comparison between a 55 million MOSFET and our 55 ICeGaN. And as you can see, the charge, the output capacitance charge, it's much higher, particularly at low voltage. So the COTR or the charge of the QSS is about 10 times more than in a MOSFET. So the MOSFET PDS discharge is significantly lower at low voltage, and ICeGaN is very clean and much faster. I found that some of the latest superjunction MOSFETs have very low COSS, even actually it can be even lower than some of the GaN devices. But the COSS value, as I said, is a value at usually 400 volts. If you take into account all the charge trapped in the drain to source capacitance, still our ICeGaN has 10 times less charge. So our ICeGaN would be much faster, and the ability to increase the frequency is without a doubt without the ICE. And here is a small analysis on the 55 milliohms devices at 500 kilohertz switching frequency. So I compare our 55 million device with two different MOSFETs, and you can see on the left the dead time versus, the magnetizing inductance versus dead time, and the magnetizing current versus dead time. And you can see that with ICeGaN, with shorter dead times, we can have also much smaller circulating current. And for example, if you choose 100 nanoseconds, we need 2 amps to discharge. We need 2 amps in the magnetizing current to discharge the output charge of the device. The circulating current will generate about 0.3 watts of losses, and a MOSFET will need like 18 amps, and this will generate 3 watts of losses, which it might not sound very high for a very high power LLC converter, but actually it will hit the device, and also it will be more relevant at lighter loads. So in short, our ICeGaN has 10 times lower COTR, shorter time to achieve 0 voltage switching, less magnetizing current losses, less energy storage in the magnetizing inductance. And here we did we had a board in the lab that we can test different devices, we can test different synchronous rectifier, different configurations and different topologies. We use this board as a benchmark, and we create a 3 kilowatt LLC converter, this time switching out 570 kilohertz as 400 volts input, 50 volts output. The maximum output current 60 amp is, as you can see, is full bridge in the input, full bridge in the output. Uses the 55 million ICeGaN in the primary bridge, and we can achieve 98.2.15 at approximately 50% load, which is very good because the board, as you can see, the board is really big and has connectors, so it's not particularly optimized. So this can be optimized, and then we likely see the efficiency going up a little bit. We are running this converter with a PQ 4040 that Booth has helped us designing, and they manufacture and then send some samples. And actually, we are working in a new magnetic that is smaller than that. On the output rectifier, we use ICeGaN device. So this board is all GaN LLC board. And here you can see some of the waveforms. The waveforms are the currents, and the transitions of the VDS are really clean. We have a 29 microhenries magnetic inductance, frequency, as I said, 570 kilohertz. The 0 voltage switching time is about 30 nanoseconds, and then we can have we run the board with 50 nanoseconds dead time. So using this is a full load, so we have used these waveforms to calculate the losses in the ICeGaN, and is less than 5 watts, which is really good. The total losses in the primary bridge is less than 20 watts. And it's coming to, my presentation is coming to an end, so thanks very much. And this is a small summary about the ICeGaN in LLC. So first of all, and most important, we can achieve and fast higher frequency. We have fast switching, so we can achieve higher frequency operation, shorter dead times, and that allows higher power density converters. Our device is very simple to drive, doesn't need any negative drive, there's no turn-off path, layout, it's very flexible. Only 2 components per devices. Our ICeGaN is very easy to parallel and very easy to scale to high power, and we have a gate that is very, very robust. And that's it for today. Thanks very much again, and I hope you enjoy.
Yeah, thank you, Carlos, for your interesting presentation. Now we'll come to your questions. And before we start with the live Q&A session, I will share the handout from the presentation from Carlos, and then everybody can download it. Yeah. Okay. Now you can download the handout. So, Carlos, can you hear me?
Yeah, can you hear me?
Yes.
Great.
Are you ready for the questions?
Yes, I am. Yes.
Perfect.
Of course.
Perfect. Okay, then I would say we can start with the questions.
Let's go to let's go with the first one. Any automotive parts? So these parts, we don't have automotive part at the moment, but we are working on having automotive products in the next 1, 2, 3 years. So yeah, this is a market we are going to target, and we are interested on, and we think ICeGaN can have add value. Next question, not sure if I understand, but are they studying high capital duty 100%? As long as you have the BDD and you have the gate on, and don't see any problem. But if you have any more questions, you should send me an email, and maybe we can discuss this more in detail. Rob has asked, can these devices be driven by 3.3 EIO output from the micro? The answer is no. So you need a driver. So our devices have the Miller clamp inside, but they don't have the driver inside. You still need a driver, and the recommended voltage, minimum voltage to drive ICeGaN is 9 volts to activate safely the internal Miller clamp. Next question: Do we need a external gate driver for logic PWM? Well, yeah, I already asked this question. We don't have, as I said, we don't have the driver inside. You need an external driver. And PWM frequency megahertz. So we have done some internal testing, and we have. You can switch with ICeGaN. You can switch at several megahertz. So there is not a problem. The best driver on paper, you can use any standard driver. I understand some of them might have some limitations. We usually use in our boards Skyworks drivers, and we have never had that problem even switching a very high frequency, several megahertz. GaN half drive devices available. We don't have a product that is a half drive with high side and low side GaN. Well, at the moment we have only a HEMT with our ICeGaN. Is galvanic isolated wire supply necessary for a half bridge with ICeGaN? So in the LLC, it's an interesting one. So in LLC, well, it depends on your application. You might want to have an isolated BCC on the secondary. In our case, in LLC or in the LLCs we have in the lab, we just choose bootstrap and there's no problem. You obviously need to provide to the secondary BCC, but as long as you have BCC in the secondary, you can just bootstrap. You don't need isolated bias to for the high side device is if I understand the question correctly. Next one. You shown an application at PCV. Are any evaluation boards available? So the PCV that I've shown is like something we have internally from benchmarking. We can, if you contact us, we can give you more details. But there's no available as an evaluation board or reference design. We have other boards, low power, but no, for now we don't have, or we don't provide these boards for testing for customers. We might do in the future some LLC evaluation board, of course. What about switching loss during turn off? That will be still a hard transition. Yes, you can have. It's true that you can have a very turn off in the LLC. As I presented in one of the slides, because the energy in the GaN is significantly lower than the than silicon devices. This is not a problem. We even have another board which is hard switching. It's a total pole PFC, and we don't use negative drive, and we just use the ICeGaN as I said here. We drive it completely in the same way. And there are losses in this hard switching applications, but compared to silicon, it's much smaller. And in an LLC, this is a minimum contribution of the losses. You can see in that slide that it was about 5 watts. Can you hear me?
Yeah, sorry.
Can you still? Can you hear me well?
Yeah, I can hear you. Yeah, you can continue.
Okay.
Sorry.
Right. So about switching turn, how about that time? Do we need driver with that time handling, or there would be integrated half bridge part? There's no, as I said, there's no half bridge part. We don't have half bridge part products. We provide only, let's say, low side parts, and that yes, you need to at the time you need a external driver, so you need to provide at that time. You mentioned 0 voltage BSS because of the internal milliclamp. Do you specify the maximum current that it clamps in the datasheet component? I don't think we do. This is something that they can find internally, but to answer the question. But if our devices are 650 volts devices, they can switch really fast, and we have done testing with these fast dV by DTs on 650 volts, and we have never experienced a problem. They were quite reliable, to be honest. Can you talk about parasitic of GaN device compared to the silicon device? I think I answered this question in the slide, because I show already the comparison between the COSS and obviously the GaN gate charge is like 10 times lower than silicon devices. So another one, how is the gate current for a regular MOSFET compared to the power need for the used internal components of the ICeGaN? Right, okay, so ICeGaN, the gate charge is 10 times smaller than a MOSFET with the same RDS zone in general. So you need much less current to drive. And obviously, if your question is about the VDD pin, you need only like 2 milliamps in the VDD pin to activate the internal circuitry we have, like the milliclamp. So this is I could say that the one of the problems is if you increase the switching frequency with silicon, you will need much lower current. Your driver will heat up very soon. With ICeGaN, you don't have that. You need significantly less current to drive the device. And I don't think, oh, there's another question there. are there any competitors on the market for GaN fetch with the same case, also same simple driver? I don't think so. I think I don't think there's any other competitors. So we have a lot of IP in the ICeGaN. So I don't think there's other people doing that. I know there are discrete camps and there are other GaN more complicated that have the driver inside and they have other problems associated with the driver inside close to the power hand. I think the question about the pin, if the question is we are pin compatible, I don't think we are at the moment. We're now looking at this, so we might have in the future some pin compatibility with other GaN. And can you explain what do you mean by you don't need turn off path? Yeah, that's a good question. So because we have the Miller clamp inside, when I say that, is because you only need, usually if you use silicon devices, you need usually put some gate resistant value to turn on. And with the diode or with some bipolar, for example, you provide another parallel turn-on path. So with our devices, you don't need these parallel turn-on, turn-off paths, and you don't need drivers with separate turn-on or turn-on paths. You only need to drive our devices with a simple resistor that from the driver to the gates, and when you turn off, the same path, it's the same resistor, and the turn on will be hard internally with the Miller clamp. So the Miller clamp will do the hard job for you. This is why I say you don't need turn off path. You only need a path. I think are there alternative GaN available to the ICeGaN? Same print, same driving signals. Oh, I already mentioned that.
Okay. Cool. Thank you, Carlos.
Yeah,
I see no more. Yeah, I see no more questions in the chat, but many thanks for all the answers and also for the presentation. Yeah, when you had any questions left, you can write into the chat and then Carlos will answer it via email in the next days. So thank you for your attention. Please check out the digital WE days on our website. We have a lot of other sessions during this week. So yeah, we just now and stay tuned. And then I would say thank you and goodbye.